Hi everyone, I'm Alex Weaver, and I'm working with Guido Mueller and Paul Fulda at University of Florida on simulations of LISA far-field tilt-length coupling due to Zernike-based wavefront errors, as well as on recreating RX beam signals to look at tilt-length removal with DWS signals. Some of this work is being done in collaboration with Paul Edwards here at UF, as well as Mengan Zhao and Gudrun Warner at AEI Hanover. This talk is split into two parts. The first part is about far-field TX Beam TTL simulations. Simply put, our telescope and optical bench introduce some wavefront error to the outgoing beam, which leads to non-zero far-field phase gradient, which then couples with spacecraft jitter to produce deviations in our length signal. I'll be talking about an extremely fast TTL reconstruction scheme for general wavefront errors and show the contributions of individual Zernikes to tilt-to-length coupling. Something we've known for some time, but acts as a good verification of results. Here, we see a schematic of how tilt-to-length comes about in the TX beam. We have some wavefront error under lambda over 30 that propagates out and contributes to a non-spherical wavefront. As our spacecraft jitters at up to 10 nanoradians per square root hertz, perturbations in the wavefront travel up to 25 meters in the far field, walking across the receiving telescope and giving us unintended length signals. We model these tilt-to-length contributions by first decomposing the outgoing beam with wavefront error present into Hermite-Gauss modes. We propagate these modes to the far field, take the phase, and then calculate the phase gradient. From the magnitude of the phase gradient, we can calculate the maximum possible tilt-to-length coupling. For faster reconstruction techniques, we look at linearizations. However, because of the nearly spherical background phase and the nature of the magnitude, we can't linearize the total tilt-to-length magnitude. We can, however, linearize the gradient vector, and therefore the different components of tilt-to-length coupling. To the right, we see the magnitude of the coupling between various Zernikes in our wavefront error to the theta and phi tilt-to-length couplings. We see both the average couplings and the maximum couplings within a 700 nanoradian cone of the far field to account for spacecraft spatial and pointing offsets, organized by the index of Zernike coefficient in the null indexing scheme. With linearized components of the gradient, we can quickly recover the tilt-to-length associated with any map. We're currently in the process of verifying that this actually produces the correct tilt-to-length couplings. Now on to the second topic of this talk. We've also been simulating RX-LO beam signals. We take a top hat beam built out of Hermite-Gauss modes up to about order 36 and mix it with a Gaussian local oscillator beam, analytically calculating the beat signal over each section of a quadrant photodiode to create realistic DWS and LPS signals for a variety of beam and photodiode conditions. The first goal of this is to test DWS reliability over the range necessary during lock acquisition. The second goal is to test RX beam tilt angle recovery capabilities using our DWS signals. And the third goal is to test tilt-to-length coupling removal from length signals in two different LPS formulations. During lock acquisition, spacecraft control transfers from constellation acquisition system to differential wavefront sensing. We examine over which angular range DWS signal allows to align the constellation and bring us into science mode. We use our code to analyze how the effects of internal beam misalignments on our DWS signal will affect our ability to acquire lock. Recovering beam tilt angles from DWS signals or subtracting tilt-to-length from length signals requires calibration of these signals. Intentionally jittering our RX beam, we use the known jitter, LPS, and DWS to obtain central LPS and DWS slopes with respect to the beam tilt. We examine, using these slopes, the beam tilts for which we can adequately recover beam angle and remove tilt-to-length noise, looking at how these ranges vary with beam or system parameters. We do this with two different formulations of a length signal, both acting the same for true length recovery, but performing differently with beam tilts present. The first, the total LPS, treats the quadrant photodiode as a single element photodiode, combining quadrant signals before extracting the beat signal phase. This is the same type of LPS talked about by Paul Edwards in his talk. The second, the regular LPS, is what the mission currently intends to use and recovers the phase of each quadrant separately, averaging these for a length signal. We saw we were not contrast or shot noise limited over the entire range of RX angles tested, plus or minus 500 microradians on the bench, and far outside the range required during lock acquisition. This was tested for a variety of beam parameters. Below are the DWS signals in radians, the contrasts, and the shot noise to beat signal amplitude ratio, which is essentially shot phase noise in radians per square root hertz, all as functions of beam tilt in microradians with static longitudinal and lateral beam misalignments. By longitudinal, we're talking about the offset of the beam clip image in front of the photodiode, ranging from 0 to 1 centimeter. Lateral misalignments refers to a lateral shift of the RX beam, ranging from 0 to 100 micrometers. Using calibrated central DWS slopes, we see we were able to recover the angle to within a microradian of the correct beam angle for beam tilts within plus or minus 220 microradians when longitudinal offsets were present, and to within 210 microradians when lateral misalignments were present. Below are graphs of the recovered and true tilt angles, as well as the error in our recovery, all in microradians, as a function of beam tilt in microradians. Differences are only noticeable at the most extreme angles. Looking at our ability to remove tilt to length noise from length signals, we examine the ranges from which we could recover the correct length signal to within a picometer. The first set of graphs shows residual tilt to length noise in picometers, after subtraction when longitudinal offsets were present, for which subtraction was adequate within plus or minus 100 microradians of beam tilt using the total LPS scheme, and only to within plus or minus 10 microradians using the regular LPS scheme. The second two graphs again show residual tilt to length noise in picometers, but when lateral RX offsets are present. The range of success was more restricted, plus or minus 20 microradians for the total LPS and plus or minus 10 microradians for the regular. While we can sufficiently remove tilt to length using both length formulations as long as the loop controls or keeps bench RX beams alignment within 10 microradians, it appears the total LPS length scheme is more successful for reducing tilt to length coupling. We have yet to understand why, but we will continue testing in setups more consistent with LISAs to see whether we need to change how we plan to measure length signals in the mission. With these tools now in hand, we also start to look at the other misalignments and imperfections, such as misalignments of the local oscillator with respect to the photodetector, and how those affect the DWS lock acquisition range and TTL correction. This concludes today's talk. I've provided supplementary slides organized as shown to clear up any points I may not have conveyed. Thank you for your time.